Linear actuators are electric, pneumatic, or hydraulic components that impart straight motion strokes to automated designs of all types, though, unless stated otherwise, it's typically assumed electric types are being referenced when linear actuators are mentioned. Linear actuators are as ubiquitous as they are because automating machine functions along straight axes, also called Cartesian arrangements, simplifies their engineering. Many applications call for the use of electromechanical linear actuation, which includes electric motors paired with various mechanical components for controlled movement of equipment or other payloads. Options for linear actuation have proliferated in recent years. Actuators and linear motion options today are also easier than ever to integrate into machinery, and they're often less costly than in the past. Most linear actuators turn an electric motor's rotary power into linear motion in one of three ways: through a rack and pinion set, through a chain or belt via a sprocket or pulley mounted to the motor output, through a screw drive, whether ball screw, lead screw, or roller screw. A fourth option for linear actuation is linear motors, a technologically advanced direct drive method of transmitting motor power into axis linear motion. These entirely omit the mechanical linkage for rotary-to-linear conversion and instead include a moving forcer that travels along a stationary platen. Two widely used linear actuators are NEMA 17 and NEMA 23 stepper motor actuators, sometimes called motorized screws. These linear actuators are named for the standard size related designations of their electric motors. Here, standard electric rotary steppers in standard NEMA sizes pair with lead screws in imperial or metric variations to yield high linear resolutions and forces. NEMA stepper motors destined for linear actuation applications produce maximum torque when the motor is at standstill and continue to provide very high torque at speeds to thousands of RPMs in some cases. In contrast, servo motors often require a gearbox to multiply the torque and reduce the speed from the motor. Because stepper motors don't necessarily require mechanical gearing to produce high torque at low speeds, they also have an advantage in overall system stiffness for many linear actuation applications. Hybrid stepper motors are most common in industrial-grade linear motion applications. Because they produce full torque at standstill, stepper motors can hold a load in place even against external forces and run open loop. This is especially useful in processing applications, where loads are held stationary while some machining or assembly task is performed, and on other axes that need to wait for some other action to complete. For more videos like this, visit designworldonline.com/videos.